What if the most important discovery in human history didn't arrive with a signal or a spacecraft landing, but as a faint glow in the darkness that we almost ignored? Because right now, something is moving through our solar system that refuses to follow the rules, and the deeper we look, the harder it becomes to explain. This is not just another space object. This could be the moment everything changes. It is April 6th, 2026, and just hours ago, astronomers confirmed something that has unsettled even the most rational minds in science. For decades, we have scanned the cosmos searching for patterns, signals, and signs of life. Not just planets, not just stars, but anomalies. Those rare moments when reality doesn't behave the way it's supposed to. And now, the James Webb Space Telescope may have found exactly that. What started as a routine observation quickly turned into something far more serious. The target was an interstellar object known as 3I Atlas, only the third confirmed visitor from beyond our solar system. At first, it was treated like a curiosity, similar to Oumuamua and 2I Borisov. Objects like these pass through, give us a brief glimpse into other star systems, and then disappear forever. That's the pattern. That's what we expected. But 3I Atlas did not follow that pattern. From the very beginning, something felt off. Even in the earliest telescope images, its brightness didn't match its size. It was too consistent, too steady. Natural objects don't behave like that. Comets usually flare and fade as they release gas and dust when approaching the sun. But this object didn't. It maintained a controlled, stable glow, almost as if it was powered from within rather than reflecting sunlight from the outside. That single detail was enough to raise concern. But what came next made it impossible to ignore. When the James Webb Space Telescope focused its instruments on the object, scientists expected to confirm a standard explanation. Instead, they found something far more disturbing. The telescope detected a thermal signature that did not match reflected light. This wasn't sunlight bouncing off ice or dust. This was heat being generated from the inside. A central emission, radiating outward, steady but not constant. It pulsed, faintly but clearly. That pulse changed everything. Because in space, random systems don't produce rhythm like that. Random processes create noise. This was not noise. This was a pattern. As more data came in, teams across NASA and international space agencies began running models to explain what they were seeing. Some suggested radioactive decay, others proposed internal friction or unknown chemical reactions. But one by one, those explanations failed. None of them could fully account for the controlled emission, the stability, and the repeating cycles all at once. And that left scientists with a possibility they were not ready to accept. If the light is not reflected, and it is not random, then it must be generated. And if it is generated, then something is generating it. At the same time, more telescopes around the world turned toward 3I Atlas. The deeper they looked, the stranger it became. Its trajectory through space was unusually precise. Not chaotic, not slightly irregular like most natural bodies, but smooth, controlled, almost calculated. Its rotation added another layer to the mystery. It completed a full rotation every 14.2 hours, and despite increasing solar radiation, that rate did not change, not even slightly. That level of stability is extremely rare in natural objects. Then came another discovery that pushed the situation even further. The object showed no visible cometary tail, even as it moved closer to the sun. Normally, heat causes ice to vaporize, creating a glowing trail of gas and dust. But here, there was nothing. No tail, no burst of particles, no sign of typical comet behavior. It was as if something was containing it, preventing any material from escaping. That raised a serious question. Was this object simply different, or was it designed to behave this way? The data kept building, and with each new observation, the gap between known physics and what we were seeing continued to grow. Scientists began measuring its surface reflectivity, also known as albedo, and the results were shocking. Certain regions reflected light almost perfectly, similar to polished metal, not rock, not ice, but something far more refined. At this point, the conversation started to shift. Quietly, behind closed doors, new terms began to appear: probe, artifact, craft. These were not public statements. They were internal discussions, careful, cautious, but impossible to ignore. Because when an object reflects light like metal, emits internal heat, maintains perfect rotational stability, and follows a precise path through space, the word natural becomes harder to defend. And then came the most unsettling detail of all: the light itself. Detailed analysis showed that the emission was not spread across a wide spectrum like natural light. Instead, it was concentrated into narrow bands, controlled wavelengths. This is exactly how human technology operates when it comes to communication systems, whether it's lasers, LEDs, or signal beacons. It was not just light, it was structured light. And even more concerning, the intensity of that light appeared to adjust slightly depending on solar radiation, as if responding in real time. That suggests feedback, and feedback suggests awareness of the environment. At this stage, the scientific community found itself standing at a crossroads. Either this was the most unusual natural object ever discovered, something that would force a complete rewrite of astrophysics, or it was something else entirely. Something designed, something functional. And if it was designed, then one question becomes impossible to avoid: who designed it? Because whatever 3I Atlas is, it is not just drifting through space unnoticed. It is active, it is consistent, and it is behaving in ways that demand an explanation. And just when scientists thought the mystery couldn't get deeper, new data began to emerge from signal analysis, data that would push this discovery beyond observation and into something far more unsettling. If you think this is already hard to explain, stay with the next part, because what scientists discovered hidden inside the signal will take this story to an entirely different level, and if you don't want to miss it, make sure you subscribe now and keep watching. If the behavior of 3I Atlas already seemed difficult to explain, what scientists uncovered next made the situation even more complex. Because once the focus shifted from visual observation to electromagnetic analysis, a new layer of data began to reveal patterns that were not visible through telescopes alone. And hidden within that data was something that challenged the assumption that this object was purely natural. Teams from multiple institutions, including researchers at MIT and Harvard, began performing deep signal analysis on the emissions detected by the James Webb Space Telescope, along with supporting observations from ground-based arrays and other orbital instruments. At first glance, the electromagnetic readings appeared inconsistent, a mixture of noise and scattered frequencies across a wide range of the spectrum. Nothing unusual at that stage, at least not immediately. But the deeper they analyzed the data, the more structured it became. Using Fourier transforms and other frequency decomposition methods, researchers isolated repeating components buried within the broader signal. These were not obvious at first, but once extracted, they revealed a pattern of pulses that repeated with a level of precision that did not align with natural randomness. The intervals between these pulses were consistent enough to suggest intentional structure rather than chaotic emission. This discovery shifted the interpretation of the data significantly, because in natural systems, repetition occurs, but not with such stability across long periods of observation. What scientists were seeing was not just repetition, but order, and order within a signal often points to a system that is controlling the output rather than generating it passively. At this point, several hypotheses were proposed to explain the phenomenon. Some researchers suggested that the pulses could be the result of a rotating object with uneven thermal properties, where different regions emit energy as they rotate into view. Others considered the possibility of a power source operating internally, cycling through phases of energy release. There were even discussions about exotic materials, or unknown isotopes, that might produce irregular emissions under certain conditions. However, none of these explanations fully accounted for all aspects of the signal. What made the situation more intriguing was the narrow band in which the emissions were concentrated. Instead of a broad, diffuse energy output, the signal appeared confined to specific frequency ranges. This is important because narrow-band emissions are not typical of natural cosmic sources. They are often associated with engineered systems, particularly those designed for communication or transmission. In practical terms, narrowband signals are used when information needs to be sent efficiently and with minimal interference. This is the same principle behind many human-made systems, from radio communications to laser-based data transmission. That realization led researchers to consider a more controversial possibility. Could the signal itself be carrying information? To test this idea, scientists applied additional decoding techniques, searching for structure within the pulses that might resemble known encoding systems. While the results were not definitive, some patterns showed statistical alignment with sequences that resemble binary-like structures. These weren't clear messages, but they were not entirely random either. And that ambiguity is what made the findings so compelling. Because even without a readable message, the presence of structured variation suggests that the signal may not be accidental. It may be purposeful, even if its meaning remains beyond our understanding. Meanwhile, another critical observation came from the timing of these emissions. The pulses were not constant in intensity. Instead, they showed subtle fluctuations that appeared to correlate with external factors, particularly the object's proximity to the sun. As solar radiation increased, slight adjustments in the emission pattern were detected, as if the system was compensating or adapting to environmental changes. That kind of responsiveness is not typical of inert matter. It implies a level of interaction with surroundings that goes beyond passive reflection or emission. At this stage, scientists began to consider whether the object might be maintaining some form of internal regulation system, a mechanism that monitors external conditions and adjusts outputs accordingly. In engineering terms, this is known as a feedback loop, and feedback loops are a hallmark of controlled systems. As more data accumulated, the interpretation of 3I Atlas began to evolve from a passive interstellar object into something far more dynamic. Its emissions were not just present, they were structured. Its light was not just visible, it was controlled. And its behavior was not just consistent, it appeared responsive. This led to one of the most important questions raised so far. If this object is generating signals with structure, and those signals exhibit stability, narrow frequency bands, and adaptive variation, then what is their purpose? Some researchers cautiously proposed that the object could be emitting a beacon signal, a repeating transmission designed to be detected across vast distances. Others suggested it might be telemetry, continuously sending data back to its origin point, wherever that may be. Both interpretations carry significant implications. A beacon implies intention to be found. Telemetry implies ongoing communication with a receiver. In both cases, the object is not isolated. It is part of a broader system, whether we have detected that system or not. However, one detail stood out more than the rest. The signal had not changed since it was first detected. Despite variations in environmental conditions and observational angles, the core structure of the emissions remained consistent. That stability suggested a predefined pattern rather than an evolving one. In other words, whatever was generating the signal was not improvising, it was following a fixed design, and that raises a deeper possibility. If the signal is fixed, then it may not be intended for us specifically. It could be a repeating broadcast meant for a different receiver, one that operates on the same parameters as the source. At this point, scientists were forced to confront a thought that had been quietly forming in the background of their analysis. What if we are not the intended audience? Because while we are now detecting and analyzing the emissions, there is no evidence that the signal was created with human detection in mind. It may have existed long before we noticed it, transmitting continuously across space, waiting for a receiver that matches its intended system. And if that is true, then our discovery of the signal may not mark the beginning of communication. It may simply mark the moment we became aware of something that has been active all along. As research continued, attention began to shift toward combining these electromagnetic findings with the object's physical behavior. And when those two datasets were compared, the picture that emerged suggested something even more deliberate than previously imagined, leading scientists to reconsider not just what the object is doing, but why it is here at all. As physical observations and signal analysis began to align, scientists realized they were no longer dealing with isolated anomalies. Instead, they were seeing a consistent pattern across multiple layers of data. The object's motion, its emissions, and its structural properties all seemed to reinforce the same conclusion. This was not behaving like a typical interstellar body, and the more they studied it, the more its behavior appeared coordinated rather than random. Attention first returned to its trajectory. When plotted against known gravitational influences, the path of 3I Atlas appeared smooth at a glance, but detailed modeling revealed subtle deviations that could not be fully explained by natural forces alone. Gravitational pull from the Sun and nearby planets accounted for most of its motion, but not all of it. Small adjustments in its course suggested the presence of additional influence, however minimal. These deviations were not abrupt. They were gradual, almost imperceptible, yet consistent enough to be measured across multiple observations. When researchers compared predictions with actual tracking data, the object repeatedly stayed just slightly off expected trajectories, as if correcting its path in tiny increments. This raised an important question. If an object can make even minor adjustments to its trajectory, then it is no longer purely passive. It is interacting with its environment in a controlled way. At the same time, its rotational behavior continued to defy expectations. Despite external forces acting on it, the rotation remained stable and predictable. In natural objects, rotation often changes due to uneven mass distribution or external torques. Over time, these influences cause wobbling or drift. But 3I Atlas maintained a steady rotational period with minimal variation, suggesting internal regulation or structural design that preserves balance. This level of stability, combined with the earlier findings of internal heat emission and structured light output, began to form a coherent profile. Each individual observation might have been explainable on its own under certain assumptions, but together they pointed towards something more organized. Then came the issue of its surface properties. Spectroscopic readings indicated that parts of the object's surface had unusually high reflectivity, approaching levels associated with polished metallic materials. This was not uniform across the entire object, but certain regions displayed characteristics that stood out sharply against the expected composition of a natural interstellar body. Natural objects, especially those composed of rock, ice, or mixed materials, tend to have irregular surfaces with varying reflectivity. Their albedo changes depending on composition and texture. But in this case, the reflectivity was not only high in certain areas, it was also consistent within those regions, suggesting a level of uniformity that is uncommon in naturally formed structures. This led researchers to consider whether the object might have layered construction, a surface that is not entirely natural, but potentially modified or covered by materials designed to serve a specific function. One possibility discussed was that the outer layer could be acting as a protective shell, shielding internal components from radiation or micrometeoroid impacts during interstellar travel. If true, this would imply a level of durability and purpose beyond natural formation. At the same time, the absence of a cometary tail continued to stand out. Even as the object approached regions where solar heating increased, there was no significant release of gas or debris. In typical comets, this process is one of the most visible indicators of activity. The lack of such a feature suggested that either the object contained very little volatile material or that something was preventing it from escaping. Combined with the earlier observations of stable rotation and internal heat, this absence began to look less like coincidence and more like control. As more data accumulated, scientists began comparing these findings against known categories of interstellar objects. Neither asteroids nor comets fully matched the observed behavior. The object did not fit cleanly into any existing classification. It shared traits with multiple types of bodies, yet aligned completely with none. This classification challenge is not unusual in astronomy when encountering new phenomena. However, in this case, the inconsistencies were not minor deviations, they were fundamental differences in behavior. At this point, researchers began to broaden their perspective beyond natural explanations. Discussions shifted toward the possibility that the object might be artificial in origin, not as a definitive conclusion, but as a hypothesis that could explain multiple anomalies simultaneously. Within academic and institutional circles, certain terms began to appear more frequently in internal discussions. Words like probe, platform, and even artifact were used cautiously to describe the object, not as confirmed labels, but as conceptual frameworks to organize the data. The reasoning behind these terms was straightforward. If an object is structured, stable, emits energy in controlled patterns, and follows a precise trajectory, then it may not be simply passing through space. It could be designed to perform a function, and if it has a function, then its presence in our solar system may not be accidental. Another detail added weight to this line of thinking. The object's approach into the solar system followed a path that brought it through regions where planetary alignments and gravitational influences could be observed effectively. From a purely observational standpoint, this trajectory would allow a passing object to gather data on multiple celestial bodies in a relatively efficient manner. While this could be coincidental, some researchers noted that the alignment of its path with key regions of interest seemed unusually well positioned. Not perfect, but notable enough to warrant attention. As discussions continued, the idea that 3I Atlas might be operating as a probe began to gain cautious consideration. A probe, in this context, would be an object designed to travel between star systems, collect data, and possibly transmit that data back to a source or repository. Such concepts are not purely speculative. They have been studied in theoretical astrophysics as potential methods for long-term exploration of the galaxy. Autonomous probes could, in theory, operate for centuries or longer, traveling between systems without requiring constant intervention. If 3I Atlas fits this category, then its current activity could represent a phase of operation triggered upon entering a system of interest. That possibility reframed the entire situation. Instead of asking why the object is behaving unusually, scientists began asking whether its behavior is part of a predefined operational cycle, and if so, then its presence in our solar system may not be random at all. It may be intentional. And with that realization, a more unsettling question emerged. If this object is designed to observe, then what exactly is it observing? As the possibility of intentional design gained more attention, researchers began to look at 3I Atlas not just as an object, but as a system with potential objectives. because if its behavior is part of a structured operational cycle, then each observed anomaly may not be an isolated event, but part of a larger pattern serving a purpose. And understanding that purpose became the next major focus. One of the first areas revisited was the object's internal energy behavior. The earlier detection of a central heat signature had already suggested that energy was being produced or managed internally rather than simply absorbed from external sources. Now, with additional data, scientists began exploring how that energy might be distributed or utilized within the object. The consistency of the thermal emission, combined with its slight pulsing pattern, suggested more than simple heat generation. It pointed toward regulation. In engineered systems, heat is often managed through cycles of activity, where energy is stored, released, or redirected, depending on operational needs. The presence of such patterns in 3I Atlas raised the possibility that internal processes were not only active but coordinated. At the same time, the object's interaction with solar radiation offered another clue. As it moved closer to the Sun, subtle changes in its emission patterns were observed. These adjustments were not dramatic, but they were measurable. This indicated that the object was responding to external energy input in a controlled manner. Rather than passively absorbing energy, it appeared to modulate its output in relation to its environment. That kind of interaction is typically associated with systems designed to manage energy flow, possibly for storage, conversion, or transmission purposes. This led to a broader hypothesis. Some researchers proposed that 3I Atlas might be capable of harvesting solar energy. If the object contains internal structures designed to collect and store energy from stars, then its journey through a solar system could serve a functional role beyond observation. It could be refueling, recharging, or sustaining its operational systems using stellar radiation. Such a mechanism would explain several of its observed characteristics. The stable thermal emissions, the lack of volatile outgassing, and the consistent light patterns could all align with a system that is actively managing energy rather than reacting passively to external forces. In this context, the absence of a cometary tail becomes even more significant. If the object is designed to capture and regulate energy, it may also be designed to contain materials within a controlled structure, preventing the release of particles that would normally occur under solar heating. This containment could serve both functional and protective purposes. As researchers examined these possibilities, another observation added further complexity. The object's light emissions appeared to fluctuate in intensity in a way that correlated with its position relative to the Sun. These fluctuations were not random. They followed a pattern that suggested adaptation rather than instability. In engineering terms, adaptive systems adjust their behavior based on input signals. If 3I Atlas is responding to solar input in a measured way, then it may be operating with a form of internal feedback control. This would allow it to maintain stability while optimizing energy usage under changing conditions. At this point, the discussion among scientists began to shift from isolated observations to system-level interpretations. Instead of analyzing each anomaly independently, they started considering how all the observed features might work together as components of a unified mechanism.